All right. The purpose of this video is going to be to just continue going over those example problems from class. So these are the problems that are in the PowerPoint that we went over in class. This is the in-class example problems document where I just have them organized into a document. And this is available for every chapter if you want to print these out and bring these to class, or if you just want to use the lecture slides, either way. But I wanted to make sure that we all had a very clear understanding of how to solve these mole conversion problems because of how essential these will be moving forward. So let's do some practice here. We went over these first several problems here. And then these next few problems are some example problems dealing with multi-step and single-step dimensional analysis. So let's start with these ones here. Calculate the number of copper atoms in 2.45 moles of copper. So 2.45 moles of copper is our quantity. Remember, a mole is just like saying a dozen. So we don't have 2.45 dozen copper atoms. We have 2.45 moles of copper atoms. And we know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. We know that that is the definition of a mole. Just like a dozen is 12, a mole is 6.02 times 10 to the 23rd. So if we want to know the number of atoms in 2.45 moles, well, we're going to start with our 2.45 moles because that's the quantity that we have. We know that we want to convert this. We want to convert this into atoms. So I'm starting with moles. I want to end up with atoms. I'm going to use that conversion that 1 mole is equal to 6.02 times 10 to the 23rd atoms. I'm starting with moles, so I put mole in the denominator. 6.02 times 10 to the 23rd atoms of copper. Copper is Cu, the elemental symbol, so I can add that to my unit here, just to be clear. Atoms of copper. So now all I need to do is 2.45 times 6.02 times 10 to the 23rd in order to get my answer. So from my calculator, I get 1.4749 E24. That E24 meaning times 10 to the 24th. My given has 3 significant figures, 1, 2, 3. So I should round my answer also to 3. I'm going to report this as 1.47 times 10 to the 24th atoms of copper. And if you're getting an answer that is off by an order of magnitude, meaning you're getting like 1.47 times 10 to the 23rd or 25th, it's likely an issue with how you are typing your numbers into your calculator. So please get some assistance with that from me, from the internet, from one of the tutors or peer leaders or somebody else in the class, anything that you need to do to get assistance with that, because you want to make sure that you're typing these into your calculator correctly. Some calculators are a little different. So again, it's something you want to practice to make sure that you know how to consistently enter these into your calculator correctly so that you're not making order of operations errors with the exponent there. All right, so move on to the next one here. 2.80 times 10 to the 22nd silver atoms. And we want to know, we want to know how many moles of silver atoms this contains. So we've got a given quantity of atoms, 2.80 times 10 to the 22nd atoms of silver. Silver has the elemental symbol Ag. Because we're just converting between atoms and moles, really the identity of this doesn't matter. It'd be like converting between numbers and dozens. It doesn't matter what it's of. The relationship is always the same. So we're just going to use this relationship again, except in this case, we need to cancel out atoms because we're starting with atoms. So I'm going to put 6.02 times 10 to the 23rd atoms of silver, and that is equal to 1 mole of silver. And that's all to solve this problem. My units of atoms of silver cancel, and my unit for my answer will be moles. So converting between atoms and moles, moles and atoms, we just use that relationship that 1 mole is by definition 6.02 times 10 to the 23rd of that thing. So 2.8 times 10 to the 22nd, again, be careful with your calculator, divided by 6.02 times 10 to the 23rd. And I get 0.0465 out of my calculator, 0.04651, a bunch of other stuff after that. So I'm going to round this to 3 significant figures, these 3 here. I don't need to round that 5 up. And because this number is small, I'm just going to report this in scientific notation. So 4.65 times 10 to the negative second moles of silver. 3 significant figures in my answer. Using scientific notation just for clarity, if you wanted to report this as 0.0465, that's fine. Once you get beyond, to the negative second, I would say definitely shift over to scientific notation. But because we're going to be using scientific notation so heavily, it is helpful just to get comfortable with it. So this is how I would report my answer here. All right, let's keep going. How many moles of aluminum are present in a sample weighing 4.50 grams? So grams to moles, this is where it depends on the substance. So 1 mole we know is 6.02 times 10 to the 23rd atoms by definition, but how much that mole weighs depends on the substance. So in this case, we've got aluminum. Aluminum has its own molar mass because the mass of an aluminum atom is different than the mass of all of our other atoms. So a mole of aluminum weighs a different amount than all of our other moles of elements. So in this case, because we're going to be converting between grams and moles, our given is a mass, 4.50 grams of aluminum, and we want to convert this into sorry, got ahead of myself with my writing. We want moles of aluminum. If you're converting between mass in grams and moles, what you need is the molar mass, right? That's why it's called the molar mass. It's the mass of 1 mole. We get that information from the periodic table. So what the periodic table tells me is that 1 mole of aluminum has a mass of 26.98 grams. That's what I'm told from the periodic table. The molar mass is on the periodic table, and it's the equivalent relationship telling you how much 1 mole of aluminum weighs. And we also know that 1 mole is 6.02 times 10 to the 23rd atoms of aluminum. But we don't actually need that information in order to answer this problem. We're just going to use this part of the relationship here, that 1 mole is 26.98 grams of aluminum. So using the molar mass of aluminum from the periodic table, I am able to put grams in the denominator. I need grams of aluminum in the denominator and moles of aluminum in the numerator. So then I just fill in the molar mass. So grams, 26.98 grams of aluminum is equal to 1 mole of aluminum. That's the mass of 1 mole of aluminum. So now all I need to do is divide 4.5 divided by 26.98. And from my calculator, I get 0.16679. So 0.16679, bunch of other stuff. I'm going to round this to 3 significant figures based on my given. So I can report this as 0.167 moles here. So rounding up this last digit based on the fact that there was a higher than 5 number after it. So just rounding that up, 0.167 moles of aluminum is my answer here. So if you're converting between mass and moles, you need the molar mass. And the molar mass depends on the substance you're dealing with, and it is in the periodic table. That's where we get that information. So lastly here, what is the mass of 2.55 moles of helium? So again, mass and moles is what I'm dealing with. So if I'm converting between mass and moles, I should use the molar mass. That's why it's called the molar mass. We use it to convert between moles and mass. So the molar mass of helium is 4.00 grams of helium are equal to 1 mole of helium. So that is the mass of 1 mole of helium. It's the mass of 6.02 times 10 to the 23rd atoms of helium. So I've got 2.55 moles of helium as my given. I want to convert this to grams of helium. So I'm going to put the unit that I have in the denominator, moles of helium, and the unit that I want in the numerator, grams of helium. And 1 mole of helium has a mass of 4 grams. So in this case, all I need to do, 2.55 times 4, and I get 10.2. And that is exactly 3 significant figures, so I don't need to round this one here. 10.2 grams of helium is my answer. So these are the 4 single-step conversion problems that we left off with in class. Let's go to the multi-step conversion problems. So we did these 2 examples with tungsten and copper. We did those ones in class, but we did not do these 4. So let's try these ones out. And these ones are going to require you to do maybe several different steps, so involving our conversions from last chapter as well. So here, we want to know how many nitrogen atoms are in a sample that weighs 4.56 kilograms. All right, so our given quantity is our 4.56 kilograms of nitrogen, which has the elemental symbol N. And we want to convert that to atoms. So eventually we need this to be atoms of nitrogen. So we want to plan out a strategy here. So we have kilograms of nitrogen. We eventually want to get to atoms of nitrogen. Well, I know a few things, and I can write those things down to remind myself. I know that 1 mole is always equal to 6.02 times 10 to the 23rd atoms. So that means that if I need to get to the unit of atoms, I can go through moles. So what that means for me is that if I convert to moles of nitrogen, then I can get atoms of nitrogen. So what I need to do is convert my kilograms into moles. So I want to think of what other relationships that I know. Well, from the periodic table, I know that 1 mole of nitrogen has a molar mass of 14.01 grams. So if I can convert my kilograms of nitrogen into grams of nitrogen, then I can convert my grams of nitrogen to moles of nitrogen and my moles to atoms. And if you wanted to go straight from grams to atoms, that's fine as well, because they are both equivalent to 1 mole. I'm just going to write out all of the steps in this case. So let's do it. We're following the units to get to our answer. This is where it can be tricky to know what to do at each step. So let's write out our units first. Let's just go units first. So kilograms of nitrogen, I can convert that into grams of nitrogen. The reason I can do that is because I know that 1 kilogram is equal to 10 to the 3rd grams. That's the definition of kilo. Kilo means 10 to the 3rd, so 1 kilogram equals 10 to the 3rd gram. So wonderful, I know I can do that conversion. And then my next set, I'm going to have to put grams of nitrogen in the denominator. And I know the relationship between grams and moles, so I can convert to moles of nitrogen. And then lastly, I want to get rid of my moles of nitrogen and convert to atoms of nitrogen. And I can do that because I know the relationship between moles and atoms here. So now all I have to do is plug in the numbers that make the denominator equal to the numerator. So 1 kilogram is equal to 10 to the 3rd grams. That's the definition of a kilogram. 1 kilo, anything, is 10 to the 3rd of that thing. So just taking kilo and making it 10 to the 3rd. So that gets rid of my kilograms, converts me to grams. From the periodic table, I know that 14.01 grams of nitrogen is the mass of 1 mole of nitrogen. So that cancels out my grams of nitrogen. And then the definition of 1 mole is that it is 6.02 times 10 to the 23rd atoms. So now my moles cancel and I'm left with atoms. So this is how I can do that multi-step conversion. And now I just have to multiply and divide across. And again, be careful here with your calculator. So 4.56 times 1,000 times 10 to the third divided by 14.01 times 6.02 times 10 to the 23rd. And what I get from this is 1.9594, and then a bunch of other stuff, E26. So I am going to round this to 1.96 times 10 to the 26th atoms of nitrogen, making sure that I've got my unit. The unit here is atoms. So we need to write out the word atoms to indicate the unit. And when you're doing calculations that have this many numbers, I think it's helpful to just type this into your calculator twice, just to make sure that you didn't make a mistake. If you're on a quiz or an exam, just take the extra second to type this into your calculator to make sure that you did get the correct answer. And so I just actually typed it into mine a second time, and we are looking good. This is the correct answer here. So let's try another. How many carbon atoms? So I'm looking for an answer that is atoms of carbon. So something over here is going to be atoms of carbon. And I have 1.3 carats of diamonds. And I'm told that a carat is 0.2 grams. So it looks like I'll be able to convert from carat to grams. I have that conversion. I'm given the conversion 1 carat is 0.20 grams. So I can use that equivalent relationship to convert between carats and grams. And then once I know grams, I've got to get to atoms. I can either do this by going grams to moles to atoms, or if we wanted, we could just go grams straight to atoms because we know that the molar mass is the mass of 6.02 times 10 to the 23rd atoms. So either of those is fine, but that carat to gram is the first step here. So I've got 1.3 carat of diamond. Diamonds, we're told, are carbon. So we're dealing with carbons. So 1.3 carats of carbon. And I'm told in my conversion that 1 carat is 0.20 grams of carbon. So now I have gotten rid of the unit of carats and I have the unit of grams here. So converting from grams to moles, this is where I've got to use my periodic table. So looking at the periodic table, to convert from grams to moles, well, the periodic table tells me that 1 mole of carbon has a mass of 12.01 grams. And we know that this 12.01 grams is also, because it's the mass of 1 mole, the mass of 6.02 times 10 to the 23rd atoms of carbon. So we can use these relationships to then find out the number of atoms of carbon in this sample. So let's go ahead and do that. So my final 2 steps here, I'm going to be converting my grams of carbon to moles of carbon, and then my moles of carbon to atoms of carbon. So my relationship is that there are 12.01 grams of carbon in 1 mole. That's from the periodic table. And I also know that the definition of 1 mole is 6.02 times 10 to the 23rd atoms. So all of my conversions here, again, based in equivalent relationships, 1 carat is equal to 0.0 or 0.20 grams. Great. 12.01 grams is equal to 1 mole. And then my units of mole cancel because 1 mole is equal to 6.02 times 10 to the 23rd atoms. So each of your conversions is based in an equivalent relationship. This equivalent relationship, this first one was given. This one was from the periodic table, and this one is the definition of a mole. So I'm going to take my 1.3 carats, multiply that times 0.2 grams, divide by 12.01 grams, and multiply by 6.02 times 10 to the 23rd. So from my calculator, I get big long number 1.3032, bunch of other stuff, E22. Can't forget about that E22. So I'm going to report this with two significant figures based on my given here. Interestingly, it's the same two numbers. So 1.3 times 10 to the 22nd atoms of carbon. 1.3 times 10 to the 22nd atoms of carbon. And that is my answer here. Reported with two significant figures based on my given having two significant figures. All right, I'm just going to erase this down here so we can answer this last question. Oh, second to last question. So we want to determine the number of atoms in 1.85 milliliters of mercury, 1.85 milliliters of mercury, and we're given the density of mercury. Remember, when you're given a density, you can read this density, 13.5 grams of mercury. Mercury has the elemental symbol Hg, is equal to 1 milliliter of Hg. That's what the density is telling me. It's telling me that equivalent relationship. So I'm given that relationship and I want to find atoms. So let's map this out. So I am given milliliters of mercury. I can convert that to grams of mercury because I have the density. The density allows you to convert between mass and volume. Then I can convert from grams of mercury into moles of mercury because my target is atoms of mercury. So these are my conversions that I can make, and just filling in my values here from the periodic table. Well, 1 mole of mercury has a molar mass of, let's take a look, mercury Hg, elemental number 80, 200.59 grams of mercury. And this is also by definition equal to 6.02 times 10 to the 23rd atoms of mercury. That's the definition of a mole. So we can use this combination of information of equivalent relationships to do these conversions. So let's start with our 1.85 milliliters of mercury. And we're going to start by using the density to convert milliliters of mercury to grams of mercury. So the density is given right here. So 1 milliliter of mercury will have a mass of 13.5 grams of mercury. So 1 milliliter of mercury has a mass of 13.5 grams. We can use that to convert our 1.85 milliliters into grams. And then we can use the molar mass to convert from grams of mercury to moles of mercury. So converting between grams and moles is what we use the molar mass for. So 200.59 grams of mercury, that is the mass of 1 mole of mercury. And by definition, we also know that 1 mole of mercury is 6.02 times 10 to the 23rd atoms of mercury. So another 3-step conversion here. We converted from milliliters to grams using the density. We convert from grams to moles using the molar mass, and we convert from moles to atoms using the definition of a mole. So I'll do 1.85 times 13.5 divided by 200.59 and times 6.02 times 10 to the 23rd. And I end up with 7.4953, bunch of other stuff, E22. So I will round this answer to 3 significant figures. 1, 2, 3, gonna round up. So this is gonna be 7.50 times 10 to the 22nd atoms of mercury. 7.50 times 10 to the 22nd atoms of mercury is my answer here. All right, again, I'm going to erase this just so I've got space for the next problem. So this one, a little bit tricky. A 20-gram sample of an element contains 4.95 times 10 to the 23rd atoms. Identify the element. Identify the element. Well, how can we differentiate the elements in a way that we can identify them? What feature do they have that makes them different? So each element has a different molar mass. So if we can calculate the molar mass of this sample, we know the mass and we know the number of atoms. If we can calculate the molar mass, we can identify the element. So that's what we're going to do. We're going to calculate the molar mass. And what is the molar mass? The molar mass is the mass of 1 mole. So the molar mass is the grams over the moles. So just like if you needed to find a density, density has units of grams per milliliter. Density, to find a density, you divide the mass by the volume. It's the same principle here. Molar mass has units of grams per mole. It's the mass of 1 mole, just like the density is the mass of 1 milliliter. So if we want to find the molar mass, we just need to divide. We're told it's a 20-gram sample. We don't know the element. We need to divide that by the number of moles. But we don't have the number of moles. We have the number of atoms. But fortunately, I can convert atoms to moles. So that's what I'm going to do here. I'm going to convert these to moles so that I can plug that in my denominator and divide the mass by the volume. So I'll just put a little dividing line here so that we know that this is a separate calculation here. So I'm going to convert my 4.95 times 10 to the 23rd atoms into moles. And to do that, all I need to do is use the definition of a mole. Well, I know that there's 6.02 times 10 to the 23rd atoms in 1 mole. So that's how I can do this conversion. So 4.95 times 10 to the 23rd divided by 6.02 times 10 to the 23rd also. And I end up with 0.822259, and then a bunch of other stuff. So I'm going to keep most of these digits. I'm not going to round just yet. Technically, we would need to round to 3 significant figures at the end, but I'm going to keep these all for now, and I'll round at the end. So I'm just saving this number in my calculator with all the digits. So 0.822259, I'm keeping all those digits in my calculator. So now that I know the number of moles, that was what I was calculating over there. So now that I know the number of moles, what I do to calculate the molar mass is I divide grams divided by moles. And what this tells me, 20 divided by that number of moles is 24.3. Now I'm reporting with correct significant figures, 3 significant figures, grams per mole. So this is the molar mass of the substance. All I did was I determined the mass of the sample, which was given, and I knew the number of atoms in the sample, so I could convert those atoms to moles and then divide the mass divided by the number of moles. And that gives me 24.3. So now I just want to look for an element that has a molar mass of 24.3, and oh, look, magnesium. So this element is magnesium based on the molar mass. So simple as that. All right. The next few examples are dealing with, instead of single atoms, we're dealing with compounds. So when you are determining the molar mass of a compound, what you're doing is adding up the molar masses of each element that's present in the compound. So for this first example here, C6H12O6 contains 6 carbon, 12 hydrogen, and 6 oxygen. And so in order to determine its molar mass, you'll take the molar mass of carbon times 6 plus the molar mass of hydrogen times 12 plus the molar mass of oxygen times 6, and you add them all up together. So you do want to make sure that you are able to comfortably do that. I will put the answers here. And when it says remember units, the units that we're going to use for molar mass are grams per mole. So this first one should be 180.16 grams per mole. So that's the mass of 1 mole of C6H12O6. So in other words, that's the mass of 6.02 times 10 to the 23rd molecules of C6H12O6. And I'll just, for this one, I'll write that out as well. So 1 mole of C6H12O6 has a mass of 180.16 grams. And that is also then the mass of 6.02 times 10 to the 23rd molecules, so not atoms, but molecules of C6H12O6. So 1 mole of anything is 6.02 times 10 to the 23rd of that thing. Since the thing that we're dealing with here is not a single atom, but a molecule, 1 mole of this thing is 6.02 times 10 to the 23rd molecules of the compound. And we can do a similar principle with all the rest of these. It's the exact same conversions that we got from before, just now we're using the word molecules to describe the substance, because the substance is not just an atom, it's a molecule. It's multiple atoms bound together. So Li2O, this one has a molar mass of 29.88 grams per mole. H2SO4, we've got a mass of 98.08 grams per mole. Sodium hydroxide, NaOH, 40.00 grams per mole. I'm going to use 2 decimal places in each of my molar masses just to have a good number of significant figures there. MgNO32, remember this 2 applies to everything that's in the parentheses. So we have 1 magnesium, we have 2 nitrogens, and we have 6 oxygens. So when we add this up, 148.30 grams per mole. And if based on how you rounded, your molar masses are off by like 100th of a fraction, that's fine. Just as long as they are, you know, certainly the first 3 digits should be the same, and ideally the 10th place as well. If your 100th place is off by 1 or 2, that's fine. But try to keep as many digits, try to keep at least 2 decimal places rather, in all of your molar masses when you are adding everything up. So we went over this first example dealing with calcium chloride in class, calcium chloride, CaCl2. Let's take a look, and I don't expect you at this point to know the formula for CaCl2. We will at some point, but for now, calcium chloride is CaCl2. I would give you that information. So let's try this next one. How many molecules of carbon dioxide are present in a sample weighing 10.8 grams? So my given here is a mass, 10.8 grams of CO2. And what I want is to calculate the molecules of CO2. So in order to do this, we're going to use the conversions that we already know. So we're converting between molecules and grams. This is the exact same thing that we did before with atoms and grams, except instead of atoms, we're dealing with molecules because we have a compound instead. So what I know is that 1 mole of CO2 contains 6.02 times 10 to the 23rd molecules of CO2. I know that by definition. And what I can determine from the periodic table is that 1 mole of CO2 has a mass of, and to get this, I'll add up my 12.01 grams plus 16.00 times 2. And we end up determining the molar mass of carbon dioxide is 44.01 grams of CO2. So these are the conversions that I'll use in order to go from molecules to grams, or grams to molecules in this case. So let's go ahead and plug those in. So I can convert from grams of CO2 to moles of CO2. And then I can convert from moles of CO2 to molecules of CO2. And there's no abbreviation for molecules because molecules, any abbreviation would start to look like moles. And we know that moles and molecules are not the same thing. 1 mole is 6.02 times 10 to the 23rd molecules. So very different. So we can't abbreviate the word molecule, unfortunately. We'll have to just write it all out. So 44.01 grams of CO2, that is the molar mass. So that's the mass of 1 mole. 1 mole of CO2, 6.02 times 10 to the 23rd molecules. And that's it for my setup here. So 10.8 divided by 44.01 times 6.02 times 10 to the 23rd. And I get out of my calculator 1.477, a bunch of other stuff that we don't care about, E23. And so I will round this to 3 significant figures and report 1.48 times 10 to the 23rd molecules of carbon dioxide. So converting from grams to molecules. And again, if you wanted to do this in one step, that'd be fine because 44 grams of CO2 is equal to 6.02 times 10 to the 23rd molecules of CO2 by definition, because both of those are equal to 1 mole. So that would also be an option if you wanted to do that. All right, so next, an aspirin tablet contains 325 milligrams of acetylsalicylic acid. We're given the formula for this. I wouldn't expect you to know that formula. And we want to determine the number of molecules. Well, this is really the same type of problem we just did up above, except now we're given milligrams instead of grams. And so the molar mass that we know is in terms of grams. And so if we are going to use the molar mass to convert from grams to moles, first we're going to need to convert these milligrams into grams. So 325 milligrams of acetylsalicylic acid, C9H8O4. I'm going to convert my milligrams into grams first. And 1 milligram, the prefix milli means 10 to the negative third. So 1 milligram is equal to 10 to the negative third grams. Then I can convert from grams to moles. So grams of C9H8O4 to moles of C9H8O4. And then we can convert from moles of C9H8O4 to molecules. So it takes a little bit to write out all of our work, but keeping nice organized work like this will help you to get the correct answer. So we are going to refer to the periodic table to determine that 1 mole of C9H8O4 has a molar mass of, we're going to add this all up, so 12.01 times 9 plus 1.01 times 8 plus 16.0 times 4. I get 180.17 grams. And that's my molar mass. So 1 mole of acetylsalicylic acid has a mass of 180.17 grams. And 1 mole by definition is 6.02 times 10 to the 23rd molecules. So that is it for my setup. So 325 times 10 to the negative third divided by 180.17 times 6.02 times 10 to the 23rd to get our answer. And I get 1.0859, bunch of other stuff, E21. So I will round this to 1.09 based on my 3 significant figures times 10 to the 21st molecules of CO2. Oh, sorry, not CO2, of acetylsalicylic acid, C9H8O4. And looking at the mass, 325 milligrams, that mass is less than 1 mole, right? The mass of 1 mole we determined was 180.17 grams. Oops, erase the gram. So this molar mass is the mass of 1 mole, and 1 mole is 6.02 times 10 to the 23rd molecules. Our mass is smaller than 1 mole. Our answer is also smaller than 1 mole. So that makes sense, or at least it doesn't not make sense. It's good to always check that your answers aren't irrational. If we'd gotten an answer that was more than 6.02 times 10 to the 23rd molecules, that wouldn't make sense here because we know that the mass that we're dealing with is less than the mass of 1 mole. So we can always kind of reflect back on whether our answer makes sense. All right, and in this last example here, I don't, again, yet expect you to know that dinitrogen trioxide is N2O3. Starting in a couple of chapters when we go over nomenclature, we will talk about that. And then in the future, you'd have to know that. But for now, don't worry about it. Dinitrogen trioxide, N2O3. We want to calculate this mass. We're starting with molecules. So 2.55 times 10 to the 22nd molecules of N2O3. Well, I know that 1 mole of N2O3 contains 6.02 times 10 to the 23rd molecules. Oops. So I can use that as my first conversion to convert from molecules to moles. Once I know moles, I know that 1 mole of N2O3 has a specific mass according to the periodic table that I will calculate, and then we can use that to convert from moles to grams. So adding that up on the periodic table, 14.01 times 2 plus 16 times 3, we get a molar mass of 76.02 grams per mole. And so plugging this in, my number of molecules that I have is less than 1 mole. So the mass that I get should be less than 76.02, just as thinking ahead. So 2.55 times 10 to the 22nd divided by 6.02 times 10 to the 23rd times 76.02, and we end up with 3.22 grams, rounded to 3 sig figs. So 3.22 grams of N2O3. And that is how we can convert from molecules to grams. So that is it as far as the math. Again, the conversions are the same. It's just getting familiar with using molecules, with using moles, with using mass, all of those equivalent relationships. It takes some practice, so do that practice. But again, let's revisit this problem here. So why we do this is because chemistry is all about ratios. It's all about ratios. If I'm going to make sodium sulfide, I need twice as many sodium atoms as I need sulfur atoms. So if I have 5 grams of sulfur, and I know that I need twice as many sodium atoms as I have sulfur atoms, what mass of sodium will I need? Well, your first thought might be, well, I need twice as much sodium as I need sulfur. So can I just take this mass and double it? But we can't just do that because the mass of each sodium atom is different. So instead, what we need to do is figure out how many atoms is this. So I know the grams of sulfur. How many atoms of sulfur is this? And once I know the number of atoms of sulfur, I know that I need twice as many atoms of sodium. So I can just multiply that number of atoms times 2, and then I can convert to moles and to grams of sodium. So let's try that out. So I'm going to convert my 5 grams of sulfur into atoms of sulfur. I'm going to do that using the periodic table. So 32.06 grams of sulfur is the mass of 1 mole of sulfur. 1 mole of sulfur contains 6.02 times 10 to the 23rd atoms of sulfur. And then, so what my balanced chemical equation is telling me is that I need twice as many sulfur atoms, or twice as many sodium atoms as sulfur atoms. We could keep doing this and do this in one step. I'll do it in a couple of steps for now. So let's determine the number of sulfur atoms first. So 5 divided by 32.06 times 6.02 times 10 to the 23rd, and I get 9.39 times 10 to the 22nd atoms of sulfur. So that's how many atoms of sulfur that I have. I am going to multiply this times 2. So multiplying this times 2, that is 1.88 times 10 to the 23rd atoms. And this is the number of atoms of sodium that I need. So this is the atoms of sodium needed. So if this is how many sodium atoms that I need, but I can't count out those atoms, I have to weigh them out. What I can do is determine what is the mass. So this is how many grams of sodium. So I'm going to do 1.88 times 10 to the 23rd atoms of sodium. And I am going to use my relationship that 6.02 times 10 to the 23rd atoms of sodium is 1 mole of sodium. And then I can use the molar mass. 1 mole of sodium has a molar mass of 22.99 grams of sodium. So just doing the same calculation that we did. So 1.88 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 22.99 grams. 7.18 grams of sodium is what I need here. 7.18 grams of sodium. So 5 grams of sulfur will react perfectly with 7.18 grams of sodium to make sodium sulfide, So this is kind of a longish way to address this problem. I'll just briefly, again, it's not something that you need to necessarily know how to do just yet, but I just want to show you why it is that we use all of this stuff. So what we just did above here, this is the long way of trying to figure out this type of a problem, which again is a really common problem. I'm trying to synthesize something. I need to know how much of my 2 reactants to mix together. So I've got 5 grams of sulfur. How much sodium do I need to mix with it? Well, this is a problem that we're going to do a lot when we get to something called stoichiometry. And so if you look at the math that we did in this first calculation, I multiplied by 6.02 times 10 to the 23rd. In the second calculation, I divided by 6.02 times 10 to the 23rd. So to answer this problem, I multiplied by something, but then I divided by that thing as well, which isn't really necessary. So when we do these calculations, what we do is we simplify them a little bit. So 5 grams of sulfur, I still need to convert that to moles. So 32.06 grams of sulfur is 1 mole of sulfur. But instead of converting this now to atoms and then doubling the number of atoms, what I can say from this balanced chemical equation, what I can read here is that 2 moles of sodium are needed for every 1 mole of sulfur in this reaction. That's the ratio that I need of these elements in this reaction. So 2 moles of sulfur, again, it's like saying 2 dozen atoms. 2 times 6.02 times 10 to the 23rd atoms of sodium, I need that many atoms for every 1 mole of sulfur atoms. So I can use this relationship here as my next conversion. 1 mole of sulfur will react with 2 moles of sodium. That's this step that we did here, multiplying by 2. We're multiplying by 2 here, but we're doing it as a quick conversion. And then once I know the moles of sodium, I'm just taking this last step, converting my moles to grams. 1 mole of sodium has a mass of 22.99 grams of sodium. And if we do this across, we get 7.18 grams of sodium, the exact same answer that we got before. So 5 divided by 32.06 times 2 times 22.99, and we get 7.17 in this case, probably just rounding differences. So 7.17 is what I got here. That's fine, just difference in rounding. This answer is probably more correct because up here, we rounded at this step to get this number, whereas this process down here required no rounding. So this math here is called stoichiometry. We are going to use these relationships a little bit later on, but it's dealing with chemical equations and reading chemical equations as mole ratios, as equivalent relationships telling you the number of moles of one atom of one compound that you need, one element or compound, to react with some amount of another compound. So 5 grams of sulfur will react with 7.17 grams of sodium. And that's where all of these relationships are headed. That's what we're going to be doing with these later. But for now, make sure that you're able to comfortably answer each of these practice problems dealing with grams, molecules, moles, atoms, all of that stuff. That's what you want to be able to do for the Chapter 2 quiz.